Hi, this is Professor Fernandez, and this is video 2 in lesson 26. We're talking here about the concavity and inflection points of transcendental functions. So the examples that I'll work through in this video come from Calculus Simplified. These are examples 428 and 429. We are talking about concavity and inflection points in a context of, exponential and logarithmic functions and trigonometric down here. But if you are looking for a review of concavity and inflection points in much easier context to understand, like algebraic functions, then I will send you off to videos 16.1 and 16.2, where we did concavity and inflection points, and we first talked about those concepts. So I'm going to use some of that stuff in this video, and let's dive into this first example up here. Excuse me. You'll notice that it says find the intervals of concavity and the inflection points for f and g, right? So I chose there was another function f of x here. To keep the video a little shorter, I'm going to not do that function, so I'm not going to do the f1. I'll just do the g function over here. And that will illustrate just as well what we're doing when it comes to finding concavity and inflection points for, in this case, a function involving a natural log. Okay, so how do we do that? Well, the first thing we want to figure out is what the derivative for this is. Remember, concavity and inflection points both have to do with the second derivative. So let's find what g prime of x is. This is a product of two functions, right? So I'm going to find the derivative of the first, multiply it by the second, plus the first times the derivative of the second. We're going to use facts about different derivatives of the natural log. We covered that in a previous video. I want to say it might be video 23, 22, I don't know. So look back into the series for that. But this is a power function. This is x to the 1/2. Its derivative is bring down the power and subtract 1 from it. So this is 1/2 x to the minus 1/2 times ln of x plus the square root of x. And the derivative of ln of x, that's where that content comes up from that previous video. Derivative there is 1 over x. Okay, so this is ln of x over 2 square root of x. That's this term here. And then over here, I'm going to assume that x is not 0, so that I can cancel some part of this with that. But that's okay, because when we look at the original function, right, ln of x equals 0 is not in the domain there. So from the given function itself, from the onset, we are not assuming that x can be 0. Okay, so in that sense, I can freely cancel square root of x from this x down here, and it's 1 over square root of x. That allows me to find this common denominator, and then combine this into ln of x plus 2. So 2 plus ln of x over 2 square root of x. Okay, that is the derivative. So believe it or not, we now have to find the second derivative because, again, concavity and inflection points are about the second derivative. Okay, this is now a different type of function. It is not really a product. I could write it as products, but it is more naturally a quotient. That's what we're seeing here. So I'm going to apply the quotient rule. So derivative of the top times the bottom minus the top times the derivative of the bottom. You might be wondering, why is he not taking the 2, why is the bottom not 2 square root of x? He's just looking at a square root of x. Because I'm really thinking of this now as 1/2 times ln of x plus 2 divided by square root of x. Okay, so this 1/2 is out here. And then the last part of the quotient rule, divided by the bottom squared, square root of x squared, that is x. Okay, so at this point, I can start simplifying things here. So this is 1/2. The derivative of ln of x plus 2, that's derivative here is 1 over x. Derivative of 2 is 0, so just 1 over x times square root of x. Minus ln of x plus 2, the derivative here was what we had before. It was 1 over 2 square root of x. So this looks like a little bit of a big mess, but don't worry, we will clean it up. First, let's marry this 2 and x to 2x. Let's simplify here to leave us with 1 over square root of x. And then let's put this into its own fraction, ln of x plus 2 divided by 2 square root of x. And then let's work on the numerator, which looks very much like what we just worked on earlier. Common denominator here is 2 square root of x. And then this part goes along for the ride. And then so this part just needs a 2. So that's a 2 there. Okay, this is the numerator. It gets divided by 2x. So I'm then going to go in here and just add a times 2x down here. And then finally you can see that things are simplifying, because if I distribute this negative sign here, then this will be minus ln of x minus 2, and I had the 2's go away. So I get minus ln of x over 2 and 2 is 4, and then square root of x times x, that's x to the 3/2. So this is a much simpler expression for the second derivative. So I'm going to get rid of most of this and then write down what matters for our purposes, which is that simplified form for g double prime. So g double prime of x is minus ln of x over 4x to the 3/2. Great. So having found the second derivative, right, what do we do to find the concavity and the inflection points? Well, remember, inflection points are where the x values at which the graph changes concavity. Okay, so then what's concavity? Concavity we can find using the information about the second derivative. So the second derivative test tells us that if the second derivative is positive, then the function is concave up. I should say that's the concavity test for concavity test. And then so if the second derivative is negative, then the function is concave down on whatever intervals we are looking at. So I'm going to set up a sign chart in much the same way as we did when we were trying to find local extrema, which required just the first derivative. To do that, remember, we find where the derivative, in this case the second derivative, is 0, and where it is not defined, does not exist. So there are places where the derivative is not defined in this particular example. You can see that we're dividing by 0, we're dividing by x to the 3/2. If x equals 0, we'll divide by 0, undefined. So I'm just going to put it here, and I'll mention in a second why we can throw it out, but I'll just record it there. Also, anything where x is less than or equal to 0, right? ln of any of those x values is undefined. So we have, it seems like a pretty big range of x values where it's undefined. But we go back again to the domain question, right? From the onset, we're dealing with the square root of x. So x cannot be negative. We can't take the negative, the square root of a negative number in this course. So that eliminates all the less than 0 possibilities. We're also dealing with ln of x. So that reinforces the fact that x can't be negative. It also adds the requirement that x can't be equal to 0. So throw that away, throw that away. And those are the only places where the derivative is undefined. So we don't have any places in the domain of the function where the derivative is undefined. So now then we go to this second part. I'm going to set ln of x over 4x to the 3/2 equal to 0. And I would like to figure out where this is 0. Well, that's only going to happen where the numerator is 0. So I'm asking, where is ln of x equals 0? You can do this a variety of ways. You could graph the ln of x function. So this is y equals ln of x. And note that at x equals 1, the y value is 0, and it's the only place. Or you could get rid of the natural log by doing the inverse operation, which is exponentiating, and then using the fact that e to the ln of x is just x, and that on the right-hand side, e to the 0 is 1. So a couple of ways you could do this, maybe more, but either way, we get to the same result, which is that x equals 1. And now, finally, I can come up with generate my sign chart here. X is 1. I'm going to put 0 over here, and I'm going to put a parentheses, right? We don't want to use test points here to determine the sign SIGN of G double prime. We don't want to use test points that are less than or equal to 0 for all the reasons that we just talked about. Okay, and now I just insert some values here. I'm free to choose. So how about we choose something between 0 and 1? How about half of it? So 1/2. And to the right, how about something like 2? Okay. We would be putting these numbers into the second derivative and then looking at the sign SIGN. One thing to notice is that because x is positive here, if I cube it and then take the square root, I will get another positive number. So the denominator is never going to change the sign SIGN of whatever test candidate x value I put in this range. The numerator is a little different. the graph of ln I just showed you looks like this. So this is y equals ln of x. So if we substitute anything into ln of x that is between 0 and 1, we get negative numbers. Okay, but there's a negative sign here. So negative, negative, so that makes it positive. So in particular, all over here, the values of g double prime are positive. Over here, these are values bigger than 1. If we substitute an x value bigger than 1 into ln, we get all of these positive numbers. So this would be positive, but then times a negative would give me a negative number. So I put negatives over here. All right, and now, based on the concavity test, we can then conclude that the function g is concave up for between 0 and 1, and concave down between 1 and off to infinity. Okay, and finally, we can say that because the function changes concavity, right, as we cross x equals 1, then x equals 1 is an inflection point. All right, so we answered the questions that were posed, and so we have finished this example. Awesome, so let's erase all this, and then let's take a look at the second example down here. This one is, I wouldn't say harder or easier, this is just different because we're dealing with trig functions now, not exponentials or logs. Okay, so here the function is 2 cosine x plus cosine squared, and we're given a specific interval here from 0 to 2 pi. So we're restricted in our interval. Find the intervals of concavity and the inflection points, same question. So I'm going to start with the white space above here so I can use that. So I don't have to run out of too much room. So first thing we want to do is calculate the derivative, f prime of x. So the derivative of cosine is negative sine. And then cosine squared, remember, this is cosine of x squared. So to differentiate that, I'm going to use the chain rule. I'll bring down the 2, put back in the inside, multiply by the derivative of the inside, which is minus sine x. So that's chain rule step. And then I do some algebra here. Notice that both of these have a negative 2 sine x. Negative 2 sine x. So I'm going to factor that out. What I'm left with from the first term here is 1. The entire term, right, is factored out. And then over here, I'm left with plus cosine x. So that's my derivative. Okay, so what is our next step here? So we are then going to find the second derivative. Okay. So now I have a product of two functions. So I'm going to take the 2 outside, have it come along for the ride, and then differentiate the first one. That's cosine x. Multiply by the second one, and then plus the first multiplied by the derivative of the second. The derivative of 1 is 0. The derivative of cosine x is negative sine x. There we go. And then now I'm just going to simplify and collect like terms and make sure I make this look as simple as possible, because I'm going to need to set it equal to 0, figure out where it's undefined, all those steps. Okay. So I'm going to multiply out here this cosine x. I get cosine x, and then over here I get plus cosine squared x. Over here I get minus sine squared x. Okay. So this is a time when it may pay to remember some of your trig identities. Cosine squared x minus sine squared x is cosine of 2x. But that actually may or may not come in handy, right? It really depends on what you're being asked to do and just how the algebra works out. So I'm not going to use that, but I'll keep that in mind that we may need to pull in some trig identities in a minute. All right, is there any location, any x values where this is undefined? The answer is no. Cosine and sine are functions that are defined for all x, so there's none of that in this problem. Okay, how about where it's equal to 0? Well, let's find out. So I'm going to set this entire thing equal to 0. I would divide by negative 2, and then I'm left with this. Okay. This seems like a really, really difficult equation to solve for x4. But I would say let's not despair. Let's use some other trig identities, right? The first 2 terms involve cosine. The second one does not. So how about we just try to make the third term into a cosine? How would we do that? Well, remember that sine squared x plus cosine squared x equals 1. so that if I solve for, or if I move over the sine squared, I get cosine squared x equals 1 minus sine squared x. And then if I move over the 1, I get cosine squared x minus 1 equals minus sine squared x. That's exactly the term I have here. So I can use that I can substitute in this for sine squared x, or negative sine squared x, and that will leave me with plus cosine squared x minus 1 equals 0. Great, so this entire term became this, and that's over here. Awesome. And so now we've kind of accomplished our short-term objective. We have 2 cosine squared x plus cosine x minus 1 equals 0. You might say, I don't really see how this, makes life easier. And I would say, yeah, that's fair. But let's do one more thing here. Let's think creatively about the equation that we're looking at now. If I, instead of giving you this equation, if I gave you the equation 2z squared plus z minus 1 equals 0, would you know what to do? And I think it's certainly more possible that you would know what to do. You would say, oh, I can try the quadratic equation. I can maybe try to factor. There's a bunch of stuff I could try. So what I'm claiming is that this equation and that equation are basically the same. How are they the same? Well, notice that everywhere I saw a cosine, I put a z. So the translation between these two equations is z equals cosine x. And this points the way forward to solving this equation for x. We are first going to solve this equation for z, and then once we have those z values, we're going to figure out what x values, when you put them into cosine, generate the z values we got. Great, so now we're going to turn our attention, therefore, to solving this equation. Again, you could do this using the quadratic formula, or it ends up factoring. To save a little time in the video, I'll just give you what the factors are. So these are the two factors that the quadratic expression factors into. So therefore, we get z equals -1 and z equals 1/2 as the two solutions for z. All right, so I can then go back to my translator over here and say, great, when z equals 1, let's start with the first one here. When z equals -1, I'm looking for the x values such that cosine of x equals -1. Again, if z is -1, z is cosine x, and cosine x is -1. Okay, so that's one set of values I'm looking for. And then when z equals 1/2, then I'm looking for cosine x to be equal to 1/2. All right, there's a bunch of values for x that generate these outputs. There are an infinite number of them, actually, because the graph of cosine x goes on forever. But remember, we only are interested in the interval 0 to 2 pi. So if I graph the function cosine of x on that interval, it looks like this. This is 2 pi. This is 0, and this is 1, and this is -1. So where is cosine of x equal to -1? There's only one place where that happens, right? And that's x equals pi. So this generates x equals pi. And then where is cosine of x equal to 1/2? Well, so 1/2 is over here, and that's there, and that's there. So there are two places that happens. And if you remember your values on the unit circle, then you can figure out what the x value is. It's pi over 3. That's the one over here. And then the one over here, you can basically add 180 degrees to that, and that is equal to, or use reference angles, and that will give you 5 pi over 3. Okay, so that's basically 2 pi minus 5 pi minus pi over 3. All right, so I have two values from this set and one value from this set. All three of them, by design, I only drew out the graph of cosine between 0 and 2 pi. All three of them are in the interval of interest. Great. So now I have finally found the answer to this question. Where is it 0? Did that. It's 0 here and here. So now I'm going to set up my sign chart and then find values to substitute into my second derivative, which I noticed I just erased, but I'll write it back over. And then figure out where the second derivative is positive and negative, and that will tell me concavity, and figure out if that concavity changes, and that will tell me inflection points. Okay, great. So we're almost done. So let's set up our sign chart. F double prime x. Here is the sign chart. I'm going to stop at 0. That's the left endpoint of my interval. I'm going to stop at 2 pi, right endpoint of my interval, and then put all of these in between. So pi is here, pi over 3 is less than that, and 5 pi over 3 is greater than that, so somewhere over here, 5 pi over 3. Okay, and then now, as I said before, you can add all different sorts of values here. At this point, you know, if you have a calculator or Wolfram Alpha or something, you can do it that way. Or you can think about your unit circle where these values lie, right? So pi over 3 is 60 degrees, so that's pi over 3. 5 pi over 3 is, 2 pi minus pi over 3, so that's kind of 60 degrees this way. So this is 5 pi over 3. Okay, so then you have information about, you have numbers that you can pick, right? And here's pi, so pi is over here. Running out of colors here, so I'll use a different color. So that is pi, angle measure. So something in between pi over 3 and pi is pi over 2, right? So you could use pi over 2. Something in between pi and 5 pi over 3 is this one down here, 3 pi over 2. So you could do that. And then something in between 0 and pi over 3, well, that's like 30 degrees, which is pi over 6. And then something in between 5 pi over 3 and 2 pi would be 2 pi minus pi over 6, so something over here. So I'm just going to write 2 pi minus pi over 6. Okay, each one of the angle values in green is an angle value that we have sine and cosine information for. So this was just my attempt to show you that you do not need a calculator or Wolfram Alpha or something. You could, in fact, do this without a calculator, just knowing your sine and cosine values. All right, so I'm going to write down the original expression for f double prime of x. This is the one before we substituted in minus sine squared x equals cosine squared x minus 1. And then what you would do now is you would take all the values in green that I just wrote down and you would substitute them into f double prime. I'm going to skip that step to keep the video a little shorter, and I'll just tell you what results, and then we'll interpret it. So you end up getting a negative values here, positive values, positive here, and then negative there. Okay, and now we can go back to the concavity test and say, hey, because the second derivative is negative here, then the function is concave down. It's positive here, concave up, positive here, concave up, and negative here, concave down. Okay, so we have information about the concavity, right? From 0 to pi over 3, and let's see, 5 pi over 3 to 2 pi, that is a concave up. The concavity there is concave up for the function f of x, 2 cosine x plus cosine squared x. Concave down, right, is everything over here. So that's pi over 3 to pi, and let's see, pi to 3 pi over 2. Okay, great. So we've gotten our concavity information, and then all that's left to do now is the information about the inflection points. So we're looking for where the graph, the function, the graph, changes concavity. This is one of those places, goes from down to up, and this is another one of those places, up to down. So that tells us that this is an inflection point, as is this. So 2 inflection points over here, pi over 3 and 5 pi over 3. All right, so last thing to mention now that we've done both of these examples, right? One little tip is when you are doing concavity and inflection points, this is about fundamentally the second derivative. So it does pay, and we did this in this first example, but you also saw us doing it here. It does pay to simplify the function and its derivative as much as you can before you go off and calculate the second derivative. That'll just save you more time. Second tip is when you actually calculate the second derivative, notice what happened in this example, right? This is what we ended up with. It didn't look feasible for us to solve this without a calculator or something. But then by using some of the trig identities, right, we were able to get this into a form where we were able to solve it and make it more tractable. So that's my second tip, especially when it comes to trig functions. There are so many trig identities out there. it's not that you want to know them all, but you want to be proficient and comfortable enough with the basic ones, which I would say all stem from the fundamental trig identity here. And so you want to do enough examples that you can use these and see how they're used in different contexts in different ways, like we did for this one. So that, you know, when you encounter trig functions in the wild, right, and you get to a problem like this where you want to find where this is equals 0, you can draw on that knowledge of trig identities to help you out. Thanks for watching.